The SM-65 Atlas was the first operational intercontinental ballistic missile, ICBM, developed by the United States and the first member of the Atlas rocket family. It was built for the U.S. Air Force by Convair Division of General Dynamics at the Kearny Mesa Assembly Plant north of San Diego. Atlas became operational as an ICBM in October 1959 and was used as a first stage for satellite launch vehicles for half a century. The Atlas missile's warhead was over 100 times more powerful than the bomb dropped over Nagasaki in 1945. An initial development contract was given to Consolidated Vultee Aircraft, Convair, on January 16, 1951 for what was then called MX-1593. It initially had a relatively low priority. The 1953 testing of the first dry fuel H-bomb in the Soviet Union led to the project being dramatically accelerated. The initial design completed by Convair in 1953 was larger than the missile that eventually entered service. Estimated warhead weight was lowered from 8,000 pounds, 3,630 kilograms, to 3,000 pounds, 1,360 kilograms, based on highly favorable U.S. nuclear warhead tests in early 1954, and on May 14, 1954 the Atlas program was formally given the highest national priority. A major development and test contract was awarded to Convair on January 14, 1955 for a 10-foot, 3 m, diameter missile to weigh about 250,000 pounds, 113,400 kilograms. Atlas development was tightly controlled by the Air Force's Western Development Division, WDD, later part of the Air Force Ballistic Missile Division. Contracts for warhead, guidance, and propulsion were handled separately by WDD. The first successful flight of a highly instrumented Atlas missile to full range occurred November 28, 1958. Atlas ICBMs were deployed operationally from October 31, 1959 to April 12, 1965. On December 18, 1958, the launch of Atlas 10B sent the missile into orbit around the Earth, without use of an upper stage, carrying the SCORE, signal communications by orbiting relay equipment, communications payload. Atlas 10B/SCORE, at 8,750 pounds, 3,970 kilograms, was the heaviest man-made object then in orbit, the first voice relay satellite, and the first man-made object in space easily visible to the naked eye due to the large, mirror-polished stainless steel tank. This was the first flight in what would be a long career for the Atlas as a satellite launcher. Many retired Atlas ICBMs would be used as launch vehicles, most with an added spin-stabilized solid rocket motor upper stage for polar orbit military payloads. Even before its military use ended in 1965, Atlas had placed 4 Project Mercury astronauts in orbit and was becoming the foundation for a family of successful space launch vehicles, most notably Atlas Agena and Atlas Centaur. Mergers led to the acquisition of the Atlas Centaur line by Lockheed Martin, which later became part of United Launch Alliance. Today Lockheed Martin and ULA support a new Atlas rocket family based on the larger Atlas V, which still uses the unique and highly efficient Centaur upper stage. Atlas V Stage 1 is powered by a Russian RD-180 oxygen/kerosene engine and uses conventional aluminum isogrid tanks, rather than the thin wall, pressure-stabilized stainless steel tanks of the original Convair Atlas. Payload weights have increased along with launch vehicle weights over the years, so the current Atlas V family serves many of the same types of commercial, DoD, and planetary missions as earlier Atlas Centaurs. History. Shortly before his death, John von Neumann headed the top-secret von Neumann ICBM committee. Its purpose was to decide on the feasibility of building an ICBM large enough to carry a thermonuclear weapon. Von Neumann had long argued that while the technical obstacles were indeed formidable, they could be overcome in time. Events were proving him right. The weapons had become smaller, and diode transistor logic enabled the construction of compact guidance computers. Atlas A, B, C, and D had no onboard computers, but Atlas E, 1960, and F, 1961, did. The committee approved a radical reorganization and speeding up of the Atlas program. Atlas was informally classified as a stage and a half rocket. Both the central sustainer engine and the set of two booster engines were started at launch, each drawing from a single set of propellant tanks. At staging, the booster engines would be shut off and a series of mechanical and hydraulic mechanisms would close the plumbing lines to them. The booster section would then be released by a series of hydraulic clamps, aside from the early test model Atlas B, which used explosive bolts, and slide off the missile. From there on, the sustainer and verniers would operate by themselves. Booster staging took place at roughly 2 minutes into launch, although the exact timing could vary considerably depending on the model of Atlas as well as the particular mission being flown. A stage of a liquid propellant rocket is normally thought of as tanks and engine, together. The jettisoned engine, therefore, constitutes a half stage. The booster engine consisted of two large thrust chambers. On the Atlas A/B/C, one turbopump assembly powered both booster engines. On the Atlas D, the booster engines had separate pump assemblies. On the Atlas E/F, each booster turbopump also got its own gas generator. Later space launcher variants of the Atlas used the Ma-5 propulsion system with twin turbopumps on each booster engine, driven by a common gas generator. The boosters were more powerful than the sustainer engine and did most of the lifting for the first 2 minutes of flight. In addition to pitch and yaw control, they could also perform roll control in the event of a vernier failure. The sustainer engine on all Atlas variants consisted of a single thrust chamber with its own turbopump and gas generator, and two small pressure-fed vernier engines. The verniers provided roll control and final velocity trim. The total sea level thrust of all 5 thrust chambers was 360,000 lbf, 1,600 knots. For a standard Atlas D. Atlas E/F had 375,000 pounds of thrust. Total sea level thrust for these 3-engine Atlas ES and FS was 389,000 lbf, 1,730 knots. Space launcher variants of the Atlas often had performance enhancements to the engines. The stage and a half design mainly came about because of the Atlas design being finalized in the mid-1950s, at a time when engineers had not yet figured out how to air-start a rocket engine, so having all engines running at liftoff would avoid this problem. The contemporary Soviet R-7 missile used a similar design for the same reason. However, technology advanced quickly and not long after design work on Atlas was completed, Convair rival Martin proposed a solution to the air-starting problem, and their Titan I missile, developed as an Atlas backup, had a conventional 2-stage design. The first Atlas flown was the Atlas A in 1957–1958. It was a test model designed to verify the structure and propulsion system, and had no sustainer engine or separable stages. The first 3 Atlas A launches used an early Rocketdyne engine design with conical thrust chambers and only 135,000 pounds of thrust. By the 4th Atlas test, they were replaced by an improved engine design that had bell-shaped thrust chambers and 150,000 pounds of thrust. This was followed by the Atlas B and C in 1958–1959. The B had full engines and booster engine staging capability. An Atlas B was used to orbit the SCOR satellite in December 1958, which was the Atlas' first space launch. The C was a more refined model with improved, lighter weight components and a bigger LOX tank and smaller fuel tank. Finally, the Atlas D, the first operational model and the basis for all Atlas space launchers, debuted in 1959. Atlas D weighed 255,950 pounds, 116,100 kilograms, without payload, and had an empty weight of only 11,894 pounds, 5,395 kilograms. The other 95.35% was propellant. Dropping the 6,720 pounds, 3,048 kilograms, booster engine and fairing reduced the dry weight to 5,174 pounds, 2,347 kilograms, a mere 2.02% of the initial gross weight of the vehicle, still excluding payload. This very low dry weight allowed Atlas D to send its thermonuclear warhead to ranges as great as 9,000 miles, 14,500 kilometers, or orbit payloads without an upper stage. The final variants of the Atlas ICBM were the E and F, introduced in 1960-61. E and F had fully self-contained inertial navigation systems, INS, and were nearly identical to each other except for interfaces associated with their different basing modes, underground silo for F, and the fuel management system. The Atlas's complicated, unconventional design proved difficult to debug compared with rocket families such as Thor and Titan, which used conventional aircraft-style structures and two-stage setups, and there were dozens of failed launches during the early years. After watching an Atlas ICBM explode shortly after launch, Mercury astronaut Gus Grissom remarked, "Are we really going to get on top of one of those things?" The numerous failures led to Atlas being dubbed an inter-county ballistic missile by missile technicians, but by 1965 most of the problems had been worked out and it was a reliable launch vehicle. Nearly every component in the Atlas managed to fail at some point during test flights, from the engine combustion chambers to the tank pressurization system to the flight control system, but Convair engineers noted with some pride that there had never been a repeat of the same failure more than 3 times, and every component malfunction on an Atlas flight was figured out and resolved. The last major design hurdle to overcome was unstable engine thrust, which caused 3 Atlas missiles to explode on their launching stands. It was solved with the use of baffled injectors and other modifications which would prove vital to the Saturn V program, as it used a first-stage engine that was loosely derived from the Atlas booster engines. By 1965, with the second-generation Titan II having reached operational status, the Atlas was obsolete as a missile system, and was gradually phased out in the mid-1960s. Many of the retired Atlas D, E, and F missiles were used for space launches into the 1990s. Atlas, named for the Atlas of Greek mythology and the contractor's parent Atlas Corporation, got its start in 1946 with the award of an Army Air Forces research contract to Consolidated Vultee Aircraft, later Convair, for the study of a 1,500 to 5,000 mile, 2,400 to 8,000 kilometers, range missile that might, at some future date, carry a nuclear-armed warhead. At the time, the late 1940s, no missile conceived could carry even the smallest nuclear warheads then thought possible. The smallest atomic warheads were all larger than the maximum theoretical payloads of the planned long-range missiles. The Convair team was led by Carol Bossert. This was the MX-774 or Hirok project. It was for this reason that the contract was cancelled in 1947, but the Army Air Forces allowed Convair to launch the 3 almost completed research vehicles using the remaining contract funds. The 3 flights were only partially successful. However, they did show that balloon tanks and gimbaled rocket engines were valid concepts. In the mid-1950s, after practical thermonuclear weapons had been demonstrated and an independent design breakthrough drastically reduced the weight of such weapons, along with the CIA learning that the Soviet ICBM program was making progress, Atlas became a crash program of the highest national importance. The missile was originally given the military designation XB-65, thus making it a bomber. From 1955 it was redesignated SM-65, Strategic Missile 65, and, from 1962, it became CGM-16. This letter C stood for coffin or container, the rocket being stored in a semi-hardened container. It was prepared for launch by being raised and fueled in the open. The Atlas F, HGM-16, was stored vertically underground, but launched after being lifted to the surface. The penetrating lubricant WD-40 found its first use as a corrosion-inhibiting coating for the outer skin of the Atlas missile. Design. The Atlas missiles A through D used radio guidance. The missile sent information from its inertial system to a ground station by radio, and received course correction information in return. The Atlas E and F had completely autonomous inertial guidance systems. Atlas was unusual in its use of balloon tanks for fuel, made of very thin stainless steel with minimal or no rigid support structures. Pressure in the tanks provides the structural rigidity required for flight. An Atlas rocket would collapse under its own weight if not kept pressurized, and had to have 5 psi, 34 kPa, nitrogen in the tank even when not fueled. The only other known use of balloon tanks at the time of writing is the Centaur high-energy upper stage, although some rockets, such as the Falcon series, use partially pressure-supported tanks. The rocket had 2 small thrust chambers on the sides of the tank called vernier rockets. These provided fine adjustment of velocity and steering after the sustainer engine shut down. Atlas also had a staging system different from most multistage rockets, which drop both engines and fuel tanks simultaneously, before firing the next stage's engines. When the Atlas missile was being developed, there was doubt as to whether a rocket engine could be ignited in space. Therefore, the decision was made to ignite all of the Atlas engines at launch. The booster engines would be discarded, while the sustainer continued to burn. Rockets using this technique are sometimes called stage and-a-half boosters. This is made possible by the extremely light weight of the balloon tanks. The tanks make up such a small percentage of the total booster weight that the weight penalty of lifting them to orbit is less than the technical and weight penalty required to throw half of them away mid-flight. Sergei Korolev made a similar choice for the same reason in the design of the R-7, the first Soviet ICBM and the launcher of Sputnik and Vostok. The R-7 had a central sustainer section, with 4 boosters attached to its sides. All engines were started before launch, eliminating the then unexplored task of igniting a large liquid fuel engine at high altitudes. Like the Atlas, the R-7 used cryogenic oxidizer and could not be kept in the state of flight readiness indefinitely. Unlike the Atlas, the R-7 had large side boosters, which required use of an expensive launch pad and prevented launching the rocket from a silo. Variants: Convair X-11/SM-65A Atlas. The Convair X-11 was intended to be the first test bed for what became the Atlas missile, using a single sustainer rocket engine. However, it was later decided to revise the Atlas design into a 3-engine missile, and the X-11 was cancelled. It was developed into the SM-65A Atlas, or Atlas A, which was the first full-scale prototype of the Atlas missile, which first flew on June 11, 1957. Unlike later versions of the Atlas missile, the Atlas A did not feature the stage-and-a-half design. Instead, the booster engines were fixed in place, and the sustainer engine was omitted. The Atlas A conducted 8 test flights, of which 4 were successful. All test flights were conducted from Cape Canaveral Air Force Station, at either Launch Complex 12 or Launch Complex 14. Atlas A flights were powered by a single engine consisting of 2 large thrust chambers fed by a single set of turbo pumps. Convair X-12/SM-65B Atlas. The Convair X-12 was the second, more advanced test bed for the Atlas rocket program. It was designed with 2 engines, the booster engine used on the predecessor X-11 plus a sustainer engine. This combination of booster plus sustainer engines was designated the Ma-1 engine system. Ma-1 was used in Atlas B and Atlas C. Ma-1 was the direct predecessor of the Ma-2 engine system of Atlas D, which in turn was the direct predecessor of the Ma-5 engine system used in Atlas Agena and Atlas Centaur launch vehicles. The first flight of X-12, Atlas B, was in July 1958. The X-12 pioneered the use of these 1.5-stage rocket engines that became a hallmark of the Atlas rocket program. It was also the first rocket to achieve a flight distance that could be considered intercontinental when it flew 6,325 miles, 10,180 kilometers. Atlas B was first flown on July 19, 1958, and was the first version of the Atlas rocket to use the stage-and-a-half design. 10 flights were made. 9 of these were suborbital test flights of the Atlas as an intercontinental ballistic missile, with 5 successful missions and 4 failures. The 7th flight, launched on December 18, 1958, was used to place the SCORE satellite into low Earth orbit, the first space launch conducted by an Atlas rocket. All launches were conducted from Cape Canaveral Air Force Station, at Launch Complexes 11, 13, and 14. SM-65C Atlas. The SM-65C Atlas, or Atlas C, was a prototype of the Atlas missile. First flown on December 24, 1958, it was the final development version of the Atlas rocket, prior to the operational Atlas D. It was originally planned to be used as the first stage of the Atlas Able rocket, but following an explosion during a static test on September 24, 1959, this was abandoned in favor of the Atlas D. 6 flights were made, all suborbital test flights of the Atlas as an intercontinental ballistic missile, with 3 tests succeeding, and 3 failing. All launches were conducted from Cape Canaveral Air Force Station, at Launch Complex 12. SM-65D Atlas. The SM-65D Atlas, or Atlas D, was the first operational version of the Atlas missile. It first flew on April 14, 1959. Atlas D missiles were also used for orbital launches, both with upper stages, such as the RM-81 Agena, and on their own as a stage-and-a-half vehicle. The Atlas D was used for the orbital element of Project Mercury, launching 4 manned Mercury spacecraft into low Earth orbit. The modified version of the Atlas D used for Project Mercury was designated Atlas LV-3B. Atlas D launches were conducted from Cape Canaveral Air Force Station, at Launch Complexes 11, 12, 13, and 14, and Vandenberg AFB Launch Complex 576. Most Atlas D launches were suborbital missile tests, however several were used for other missions, including orbital launches of manned Mercury, and unmanned OV-1 spacecraft. 2 were also used as sounding rockets, as part of Project Fire. A number were also used with upper stages to launch satellites. Atlas D would become the basis for most Atlas satellite launchers. In 1965, when the ICBM program was ended, Convair introduced a standardized Atlas D derivative for all space launches. By 1979, Atlas space launcher variants had been whittled down to just the Atlas Centaur and some refurbished ICBMs. The launch rate of Atlases decreased in the 1980s due to the advent of the Space Shuttle, but Atlas launches continued until 2004, when the last classic Atlas with balloon tanks and the jettisonable booster section launched a ComSat for the Air Force. SM-65E Atlas. The SM-65E Atlas, or Atlas E, was the first 3-engine operational variant of the Atlas missile, the third engine resulting from splitting the 2 booster thrust chambers into separate engines with independent sets of turbopumps. It first flew on October 11, 1960, and was deployed as an operational ICBM from September 1961 until March 1965. Following retirement as an ICBM, the Atlas E, along with the Atlas F, was refurbished for orbital launches as the Atlas E/F. The last Atlas E/F launch was conducted on March 24, 1995, using a rocket which had originally been built as an Atlas E. Atlas E launches were conducted from Cape Canaveral Air Force Station, at Launch Complexes 11 and 13, and Vandenberg Air Force Base at Vandenberg AFB Operational Silo Test Facility, Vandenberg AFB Launch Complex 576 and Vandenberg AFB Space Launch Complex 3. SM-65F Atlas. The SM-65F Atlas, or Atlas F, was the final operational variant of the Atlas missile. It first flew on August 8, 1961, and was deployed as an operational ICBM between September 1962 and April 1965. Following retirement as an ICBM, the Atlas F, along with the Atlas E, was refurbished for orbital launches as the Atlas E/F. The last Atlas E/F launch to use a rocket which had originally been built as an Atlas F was conducted on June 23, 1981. Atlas F launches were conducted from Cape Canaveral Air Force Station, at Launch Complexes 11 and 13, and Vandenberg Air Force Base at OSTF-2, Vandenberg AFB Launch Complex 576 and Vandenberg AFB Space Launch Complex 3. It was also used to launch the Block I series of GPS satellites from 1978 to 1985. The last refurbished Atlas F vehicle was launched from Vandenberg AFB in 1995 carrying a satellite for the Defense Meteorological Satellite Program. Warhead. The warhead of the Atlas D was originally the GE Mk2 Heat Sink Reentry Vehicle, RV, with the W-49 thermonuclear weapon, combined weight 3,700 pounds, 1,680 kilograms, and yield of 1.44 megatons, mt. The W-49 was later placed in a Mk3 ablative RV, combined weight 2,420 pounds, 1,100 kilograms. The Atlas E and F had an Avco Mk4 RV containing a W-38 thermonuclear bomb with a yield of 3.75 mt, which was fused for either air burst or contact burst. The Mk4 RV also deployed penetration aids in the form of mylar balloons which replicated the radar signature of the Mk4 RV. The Mk4 plus W-38 had a combined weight of 4,050 pounds, 1,840 kilograms. Operational deployment. Strategic Air Command deployed 11 operational Atlas ICBM squadrons between 1959 and 1962. Each of the three missile variants, the Atlas D, E, and F series, were deployed and based in progressively more secure launchers. Atlas D deployment. To provide the United States with an interim or emergency ICBM capability, in September 1959 the Air Force deployed 3 SM-65D Atlas missiles on open launch pads at Vandenberg AFB, California, under the operational control of the 576th Strategic Missile Squadron, 704th Strategic Missile Wing. Completely exposed to the elements, the three missiles were serviced by a gantry crane. One missile was on operational alert at all times. They remained on alert until May 1, 1964. In September 1959 the first operational Atlas ICBM squadron equipped with 6 SM-65D Atlas missiles based in above-ground launchers, went on operational alert at F.E. Warren AFB, Wyoming. 3 additional Atlas D squadrons, 2 near F.E. Warren AFB, Wyoming, and 1 at Offutt AFB, Nebraska, were based in above-ground launchers that provided blast protection against overpressures of only 5 pounds per square inch, 34 kPa. These units were 389th Strategic Missile Wing, Francis E. Warren AFB, Wyoming, September 2, 1960 – July 1, 1964. 564th Strategic Missile Squadron, 6 missiles. 565th Strategic Missile Squadron, 9 missiles. 385th Bombardment, later Strategic Aerospace, Wing. Offutt AFB, Nebraska, March 30, 1961 – October 1, 1964. 549th Strategic Missile Squadron, 9 missiles. The first site at Warren for the 564th SMS consisted of 6 launchers grouped together, controlled by 2 launch operations buildings, and clustered around a central guidance control facility. This was called the 3x2 configuration. 2 launch complexes of 3 missiles each constituted a squadron. At the second Warren site for the 565th SMS and at Offutt AFB, Nebraska for the 549th SMS, the missiles were based in a 3x3 configuration. 3 launchers and 1 combined guidance control/launch facility constituted a launch complex, and 3 complexes comprised a squadron. At these later sites the combined guidance and control facility measured 107 by 121 feet, 33 by 37 m, with a partial basement. A dispersal technique of spreading the launch complexes were 20 to 30 miles, 30 to 50 kilometers, apart was also employed to reduce the risk that one powerful nuclear warhead could destroy multiple launch sites. Atlas E deployment. The SM-65E Atlas squadrons deployed later in 1961 were also deployed horizontally, but the majority of the launcher was buried underground. These launchers were designed to withstand overpressures of 25 psi, 170 kPa. These units were 92nd Bombardment, later Strategic Aerospace, Wing. Fairchild Air Force Base, Washington, September 28, 1961 – February 17, 1965. 567th Strategic Missile Squadron, 9 missiles. 21st Strategic Aerospace Division. Forbes AFB, Kansas, October 10, 1961 January 4, 1965. 548th Strategic Missile Squadron, 9 missiles. 389th Strategic Missile Wing. Francis E. Warren AFB, Wyoming, November 20, 1961 January 4, 1965. 566th Strategic Missile Squadron, 9 missiles. The major enhancement in the Atlas E was the new all-inertial system that obviated the need for ground control facilities. Since the missiles were no longer tied to a central guidance control facility, the launchers could be dispersed more widely in what was called a 1x9 configuration, with one missile silo located at one launch site each for the 9 missiles assigned to the squadron. The Atlas ES were based in semi-hard or coffin facilities that protected the missile against overpressures up to 25 psi, 170 kPa. In this arrangement the missile, its support facilities, and the launch operations building were housed in reinforced concrete structures that were buried underground, only the roofs protruded above ground level. Atlas F deployment. The 6 SM-65F Atlas squadrons were the first ICBMs to be stored vertically in underground silos. Built of heavily reinforced concrete, the huge silos were designed to protect the missiles from overpressures of up to 100 psi, 690 kPa. 310th Bombardment, later Strategic Aerospace, Wing. Schilling AFB, Kansas, September 9, 1962 February 1, 1965. 550th Strategic Missile Squadron, 12 missiles. 98th Strategic Aerospace Wing. Lincoln AFB, Nebraska, September 15, 1962 March 10, 1965. 551st Strategic Missile Squadron, 12 missiles. 11th Bombardment, later Strategic Aerospace, Wing. Altus AFB, Oklahoma, October 9, 1962 December 30, 1964. 577th Strategic Missile Squadron, 12 missiles. 96th Bombardment, later Strategic Aerospace, Wing. Dias AFB, Texas, November 15, 1962 December 1, 1964. 578th Strategic Missile Squadron, 12 missiles. 6th Bombardment, later Strategic Aerospace, Wing. Walker AFB, New Mexico, November 30, 1962 January 5, 1965. 579th Strategic Missile Squadron, 12 missiles. 820th Air, later Strategic Aerospace, Division. Plattsburgh AFB, New York, December 20, 1962 March 12, 1965. 556th Strategic Missile Squadron, 12 missiles. The Atlas F was the final and most advanced version of the Atlas ICBM and was essentially a quick-firing version of the Atlas E, modified to be stored in a vertical position inside underground concrete and steel silos. When stored, the Atlas F sat atop an elevator. If a missile was placed on alert, it was fueled with RP-1, kerosene, liquid fuel, which could be stored inside the missile for extended periods. If a decision was made to launch the missile, it was fueled with liquid oxygen. Once the liquid oxygen fueling was complete, the elevator raised the missile to the surface for launching. This method of storage allowed the Atlas F to be launched in about 10 minutes, a saving of about 5 minutes over the Atlas D and Atlas E, both of which were stored horizontally and had to be raised to a vertical position before being fueled. Service history. The number of Atlas intercontinental ballistic missiles in service, by year. CGM-16D Atlas intercontinental ballistic missiles assigned. 1959, 6. 1960, 12. 1961, 32. 1962, 32. 1963, 28. 1964, 13. CGM-16E Atlas intercontinental ballistic missiles assigned. 1961, 32. 1962, 32. 1963, 33. 1964, 30. HGM-16F Atlas intercontinental ballistic missiles assigned. 1961, 1. 1962, 80. 1963, 79. 1964, 75. Retirement. After the solid fuel LGM-30 Minuteman had become operational in early 1963, the Atlas became rapidly obsolete. By October 1964, all Atlas D missiles had been phased out, followed by the Atlas E/F in April 1965. About 350 Atlas ICBMs of all versions were built, with a peak deployment level of 129, 30D, 27E, 72F. Despite its relatively short lifespan, Atlas served as the proving ground for many new missile technologies. Perhaps more importantly, its development spawned the organization, policies, and procedures that paved the way for all of the later ICBM programs. After its retirement from operational ICBM service in 1965, the ICBMs were refurbished and used over 20 years as space launch vehicles. NASA use. Though never used for its original purpose as a weapon, Atlas was suggested for use by the United States Air Force in what became known as Project Vanguard. This suggestion was ultimately turned down as Atlas would not be operational in time and was seen by many as being too heavily connected to the military for use in the U.SS International Geophysical Year satellite attempt. The Atlas was used as the expendable launch system with both the Agena and Centaur upper stages for the Mariner space probes used to explore Mercury, Venus, and Mars, 1962-1973, and to launch 10 of the Mercury program missions, 1962-1963. Atlas saw the beginnings of its workhorse status during the Mercury Atlas missions, which resulted in Lieutenant Colonel John H. Glenn Jr. becoming the first American to orbit the Earth in 1962. Major Yuri Gagarin, a Soviet cosmonaut, was the first human in orbit in 1961. Atlas was also used throughout the mid-1960s to launch the Agena target vehicles used during the Gemini program. Direct Atlas descendants were continued to be used as satellite launch vehicles into the 21st century. An Atlas rocket is shown exploding, in the 1983 art film Koyani Scazzi, directed by Godfrey Reggio, in the penultimate shot. The vehicle shown in the movie was the first launch attempt of an Atlas Centaur in May 1962. Survivors. HGM-16F Atlas is on display at the National Museum.
Please subscribe and thanks for watching.